If a solution of lead ions is added to a solution of chloride ions, a precipitate of lead chloride forms. The equation for the reaction looks typical. If the sample is heated, the solid lead chloride goes back into solution. The reverse reaction takes place. This is an example of a reversible reaction. In the equation for such a reversible reaction, we use a bidirectional arrow.
One factor of chemistry that we haven't discussed until now is the idea of chemical equilibrium. And in the past, we would have talked about lead ions and chloride ions making lead 2 chloride, the white solid you saw. And that would have been a one-directional, if you will, arrow. It would have been just reactants going to products. But in reality, these reactions, at least most of them anyway, it's in a state of equilibrium. And what that means is that in this case, the lead 2 chloride that forms the white solid, some of it decomposes back into the ions. And this equilibrium just means that you can't really bank on just reactants going to products, or for that matter, products going to reactants. Things are going to go both ways. And most reactions actually exhibit chemical equilibrium. You don't have just reactants going to products, or you don't have just products going to reactants. You have actually a mixture of both of them. Now, the bidirectional arrow, which is written in several different ways, is going to be really helpful to us in this class. Sometimes they look like 2 half arrows, and that's that version right there. So you can kind of imagine that's like 2 half arrows, all right? Sometimes, though, you're also going to see one like this one with 2 full arrows. They mean the same thing, all right, and they're just different when you can pick which one works best for you too. But that means that you've got a state of equilibrium. And honestly, most reactions do have equilibrium. So in some ways, I feel kind of guilty starting Chemistry 223 because I've kind of been lying to you so far in Chem 221 and Chem 222, and not really lying, okay, because it's all about learning curves, man. But anyway, I haven't talked about the process of, say, products going back to reactants until now. And that's what makes Chem 223 different from Chem 221 and Chem 222. This equilibrium thing is really going to rock our world here in basically this whole quarter. And we'll see lots of examples of what you can do with it, how you can use equilibrium to affect reactions. Like if you want more product or you don't want more product, there's ways to make these things happen. Pretty cool. So in equilibrium, when you have the double-sided arrow, the bidirectional arrow, you have to realize that all these equilibrium systems are quite dynamic. They're not staying in place. It's not just reactants going to products and they're being sitting there, all right? Products then are breaking up and going back into reactants. If you do have an equilibrium, then the reaction, in theory at least, is reversible. So you say, oh, I don't really want those products to form anymore. Well, in theory, there should be some way to get the products to turn back into reactants, at least to a pretty good degree. And this is something that's both empowering and it can be kind of frustrating. If you didn't want your products to decompose and you did the wrong thing, alas, maybe it would go reverse. Another thing that's interesting about equilibrium, you can really approach these reactions now from either way. And what that means, traditionally, we've written reactants on the left and products on the right. And that's the classic chemist's way of doing things. But really, if you have an equilibrium, you can think about the quote-unquote reactants as being on the right side and the quote-unquote products being on the left side. So reversible literally means you can think about reactants going to products either way, left to right or right to left, and sometimes it'll be helpful to do both. This is an example of what's called a complex ion. And a complex ion is something we're going to talk about in Chem 223. But the important part for us right now is that cobalt, the cobalt, which is in both the pink and the blue there, cobalt can make a pink form or a blue thing. And those things are the complex ions. And this is something we'll explore in this class. So when cobalt is on the left with the COH2O6Cl2, it's pink. On the other hand, if you add some chloride to it, the chlorides push some of the waters out, and you can see on the right, you've got that blue COH2O2Cl4 negative 2 thing. That form has a blue thing. So in the picture up there, you can see that little test tube in the ice. Right now, we have the blue form of cobalt, the one on the right, all right? However, we're going to see this reaction is reversible. Like we talked about, there's no reason for us to think exclusively as reactants on the left and products on the right. So the second reaction here now, same cobalt complexes, but now we've reversed the previous reaction. This is now the blue cobalt going to the pink cobalt, all right? So in this context, we think about it as COH2O2 Cl4 -2. We'd add some water to it, ending up making COH2O6 Cl2, the original pink complex, plus 2 chlorides. So this is what it means. You can literally think about it as reactant going to product from either direction. And this is like written out kind of what's happening here.
At room temperature, a solution of cobalt chloride is pink in color. When we heat it, it gradually turns blue. If we then cool the solution in an ice bath, it turns pink again. The reaction reverses.
So in this video, you can see examples of how you can transform one complex to the other. All right, so for example, if you have the pink and you add excess chloride, you can make the blue complex. On the other hand, if you have the blue complex and you add extra water, you can end up making the pink complex. And another factor that we're going to talk about in the Chem 223 is the effect of temperature. So you can see they're adding ice, they're heating it up, color changes occur. All of these are ways you can affect an equilibrium. This is a reaction we're going to talk about a lot in the beginning part of Chem 223. It's a reaction between an iron center, an iron +3, and a polyatomic ion called thiocyanide, SCN-. And the thiocyanide pushes out one of the waters to make an iron thiocyanide complex. Now, the whole reaction is listed right here in black, all right? And actually around the irons, like we're going to see at the end of Chem 223, there's actually a whole bunch of water molecules. So the SCN- is essentially pushing out one of the waters to make this iron thiocyanide complex over here, and water is a product. We're going to usually write it, though, like this one up here at the top, which is the iron +3 and thiocyanide making the FeSCN2+ complex. And this is absolutely an equilibrium. All right, you can affect this by adding more reactants or more products and changing temperatures and stuff like that. To just realize that the actual chemicals, there's water molecules involved, but we're going to see they're not quite as important as talking about just the iron and the thiocyanide making FeSCN2+.
When a solution of iron 3 nitrate is added to a solution of sodium thiocyanate, the red-orange iron thiocyanate complex ion is formed. Although the reaction looks complete, substantial amounts of iron ion and thiocyanate ion remain unreacted in solution. When iron 3 ions contact thiocyanate ions in solution, they can react to form a complex ion, iron thiocyanate. As the reaction proceeds, product molecules can react in the reverse direction to separate and reform the original ions. Eventually, the concentrations of products and reactants become constant. At this point, the rates of the forward and reverse reactions are equal, and the system is in a state of dynamic equilibrium.
The first video on the left shows what the FeSCN2+ complex looks like. It's kind of a rusty orange, maybe red. If it's intense, sometimes I call it the Klingon blood red color. And if you're new to my teaching style, yes, I am a Star Trek person. I'll make lots of Star Trek references like Klingon blood red, but you don't have to like Star Trek to do very well in this class, so don't worry. But anyway, it's got a neat color. And more also importantly is that the iron +3 and the thiocyanide solutions were both essentially colorless. So you go from clear solutions to this kind of orange-red thing, which is really cool. Now on the right is what's happening at the atomic scale. When the iron bonds with the SCN-, that's when you see kind of the blood red color, all right? Iron bonding to water, it just makes a colorless solution. So actually, because this is an equilibrium, it's kind of like a dance. And at first iron is dancing with water, but then, ferrocyanide, and they start dancing for a while. But then iron goes, hey, maybe I want to dance with water again. So it starts dancing. Instead of dancing, of course, this would be bonding, but it's not as intense of a chemical bond, you can argue. So that's why you can kind of have this back and forth kind of interaction between things that makes this equilibrium possible. Now, in the old days, we would have just said, okay, iron plus SCN, they make a bond, makes FeSCN2 plus, and that's it. But now, in the big kids league, if you will, of Chem 223, we can see that actually this reaction, like most reactions, are equilibrium. All right, they go back and forth between the two species. So the iron-water complex becomes really an iron SCN minus kind of complex, but then eventually it bounces back to iron-water, back to iron SCN, et cetera, back and forth over and over. So equilibrium is very dynamic. These things are changing all the time on the atomic level. At first, there's a lot of action because the iron and the SCN comes together to make that blood red / orange red, whatever you want to call it, thing. But after a while, the reactants and products kind of settle down, all right? And you still have forward and reverse reactions, but that's there's like a constant state. Once equilibrium is attained, you don't have like an excess of reactants being turned into products or an excess of products going back to reactants. It's a steady state they use in science, which just means the forward and reverse reactions kind of stabilize. And when you get to this stabilization part, that's when you're at equilibrium. There's lots of examples of chemical equilibrium around us all the time, and the easiest one is just ice with liquid water. And I'm sure everybody knows you take liquid water, put it in the freezer, it becomes ice, you can use it as ice cubes, whatever. On the other hand, you take the ice cubes out, you leave it on the desktop, and whoops, now all of a sudden the water turns into a liquid, but you can put it back into the ice form. This is an equilibrium. This is a temperature-based equilibrium, all right? And that's going to be important. We'll talk about that more. But again, that really is a type of equilibrium. Another example from geology is stalactite and stalagmite formations, all right? And these are the things sometimes if you've been in a cave that kind of are coming down from the ceiling or coming from the floor up, they're pretty cool. I don't know that much about it. I'm not a geologist, but anyway, you get the idea. This is an equilibrium with a calcium carbonate, and calcium carbonate can react with water and CO2, which is a weak form of an acid, kind of, and it makes calcium ions and hydrogen carbonate ions, and this goes back and forth, and geologists will study the behavior, why it goes back and forth. Pretty cool kind of stuff.